So we have already discussed how the partial derivatives at a point, so the first partial derivative of a function of two variables, z equals to f of x, y, basically represent the gradient along each of those directions. So the partial derivative with respect to y is going to be the gradient of the function at that point along the y direction, and then x is going to be the gradient along the x direction. But how about, what if we were interested in finding the gradient in some other direction other than x or y? Because obviously we have a lot of different choices that we can have. We can have all these infinite choices here. So what if we wanted to find the gradient in a specific direction that we specify in the direction of some vector that we call, so some unit vector u. All right, so just to do a little bit of recap, a unit vector is just a vector that has unit length, so the magnitude is equal to 1. So obviously we want to find a way to use the partial derivatives to find the gradient, the amount of gradient at that point along the direction of some vector that we choose. So the first thing that we need to define is, we need to first of all find the vector that is defined by the function itself, and this is something that we call the gradient function, or nabla. So this is the nabla operator, and it's drawn as a triangle upside down. So nabla of f is going to be a vector, and it is going to have the following components. So in this case we have a function of two variables, so this is going to be partial of f with respect to x, comma, partial of f with respect to y. And if we wanted to extend this to 3 dimensions, we would have partial of f with respect to z. So what this is doing, what this operator is doing, it is essentially turning a function like this of multiple variables into a vector, and that vector has components equal to each of the partial derivatives of that function. So this is going to be very important, because remember, how do we project a vector in the direction of a unit vector? Well, we just take the dot product of those two vectors. So in essence, what we want to define is, we want to define a gradient along that direction, and that's called the directional derivative. So it's denoted by d subscript of the unit vector u of the function f at some point x naught and y naught. So basically what we're going to have is, this is going to be equal to the gradient of f evaluated at those 2 points, dot product with the unit vector in the direction that which we want to project this vector. So remember, the dot product is essentially, we multiply the each corresponding component, and then we just add them up. So this is going to be the same as saying f of x, which is the partial derivative with respect to x, times u1, which is the first component of the vector, plus f of y times u2. So that's basically how we define the value of our directional derivative in that direction. So the first example we're going to look at is the following. Let's say we have a function f of xy equals to minus 4xy minus 1 over 4x to the power of 4 minus 1 over 4 y to the power of 4. And we're going to find the directional derivative at point 1, so let's call this p1 minus 1, in the direction of the unit vector root 2 over 2 minus root 2 over 2. This is the same as saying root 2 over 2 times 1 minus 1. Alright, so basically what this is telling us is that along the xy plane, so we're going to draw the xy plane here, we're going to have a unit vector that is essentially pointing in this direction. So we're going to have 1 minus 1. So that means that this vector is pointing in 45 degrees in this direction. So the unit vector is going to have unit length, so it's going to be somewhere there. And basically we're going to find the directional derivative of the surface lying on top of this. So remember, the z-axis is projected out of the page. So if we have our surface here, then what this means is that at that point 1 minus 1, at this point we're going to find the value of that gradient in the direction of that vector. So basically at 45 degrees between the x and y axis. So that's basically what we're going to be performing with this. So first thing we need to do is obviously find the partial derivative. So let's have f of x, that's going to be equal to minus 4y minus x cubed. Then f of y is going to be equal to minus 4x minus y cubed. And then if we evaluate each of these at the point 1 minus 1, we're going to get the following values. So this one is going to be equal to 3, and this one is going to be equal to minus 3. So now, in order to find the value of the directional derivative in the direction of this unit vector, what we need to do is we need to construct our vector, our gradient vector f, which is going to be these two values. And if we evaluate it at the point 1 minus 1, then that's just going to be this. So that's going to have the components 3 minus 3. And that means that when we find the directional derivative, in this case, of f at 1 minus 1, we're going to have this dot product with u, and that's going to be equal to 3 minus 3 dot product with root 2 over 2. Remember, that's a constant, so that just gets carried out with the calculation. And then we have 1 minus 1. And then this is going to become 3 times root 2 over 2 plus minus 3 times minus root 2 over 2. And this is going to become 3 times root 2. So this is the value of the gradient at that point in the direction of this unit vector. So basically at 45 degrees between the x and y axis. And this is a really useful definition because it allows us to find essentially the gradient, the value of the gradient along any direction that we choose, so long as we can define that direction as a unit vector. Now, in the case that we were given a vector but not a unit vector, remember that for any vector, we can find the unit vector by simply dividing it. So dividing each of its components by the magnitude. So we can just find the unit vector by dividing each of its components by the magnitude. And the magnitude of a vector is simply the square root of the sum of the squares of its components. So let's say u1 squared plus u2 squared plus u3 squared. So that's basically how we do it. Now, what happens with the following question? Well, what if we wanted to find, let's say we were not given a direction, what if we wanted to find the direction in which the maximum gradient occurs? Because obviously, when we're standing, let's say we're in a mountain. So let me just erase everything here. All right, let's say we're in a mountain top. So I'm just going to try to draw this to the best of my abilities. This is a horrible mountain, but hopefully you get the idea. This is in 3 dimensions. And let's put some axes here, x, y, and z. And let's say that this is you, and you're standing at this particular point along that surface of that mountain, and then you want to see, well, I'm looking up here, and I'm seeing that this is the direction in which the maximum slope occurs. That's a maximum gradient. So how can I define that in terms of the xy, the orientation that I just chose? Because you can see, oh, well, maybe in this direction I have the minimum gradient, because that means that that's the direction in which I would fall the hardest, because obviously the slope is the highest, it is the steepest in this direction. So how do we define that? How do we find that using our definition of the gradient directional derivative? Well, the maximum directional derivative is going to be equal to the gradient of that particular function. So if the surface of this mountain is modeled by the function x of y, f of xy, then the gradient, which usually double bar or the magnitude of that vector is going to give us the maximum gradient at that point that we choose. And then the direction of the direction in which that maximum occurs is going to be in the same direction as the vector itself at that point x naught, y naught. And then the minimum is the minimum directional derivative, so that's going to occur. It's going to have the value minus magnitude of the gradient vector of our function, and then the unit vector in this case, so this minimum would occur in the direction of minus vector. So basically what we would do is we would flip over, we would change the sign on the values of this unit vector, and that would give us the direction in which this minimum occurs. So let's do an example that illustrates how this works. Let's have the function g of xy equals to y squared e to the 2x, and let's say we're standing at the point p2 minus 1. So the question is, find the maximum directional derivative and its direction, and then part B is find the minimum directional derivative at that point and its direction. So let's start off by finding the vector gradient of g. So we're going to construct the vector. This is going to be the first component is going to be the partial derivative with respect to x, so that's 2 y squared e to the 2x. Second component is going to be the partial derivative of this with respect to y, so that's going to be 2y times e to the 2x. So that's our gradient vector constructed there. And if we want to evaluate it at the point 2 minus 1, then what we're going to have is g2 minus 1. This is going to give us 2 times e to the power 4 minus 2 e to the power 4. So this is the vector that we'll be using for our calculations. And I'm going to erase this from the previous example as well. Alright, so now what we're going to do is we're going to find the magnitude of this vector at this point, 2 minus 1. So this is going to be equal to 2e to the 4 squared plus minus 2e to the 4 squared, and that reduces to square root of 8 times e to the power 4. So that's going to give us the magnitude of the directional derivative of the maximum, right? This is going to be the maximum, and then the direction is going to be given by the following. So we need to find the unit vector in the direction of this, so that's going to be, our unit vector is going to be the gradient vector at 2 minus 1 over its own magnitude, which we just found. So this is basically going to be 1 over square root of 8 e to the power 4 times the vector, so that's 2e to the 4 minus 2e to the power 4. And then we can simplify this by cancelling these terms out, and then in the end we're going to get 1 over square root of 2, because we can reduce this to 2 square root of 2 e to the 4. So this is 1 minus 1. So that's going to be the direction in which this maximum occurs. And now for part B, we're going to have what's the minimum? Well, the minimum is just going to be this magnitude, but we're going to multiply it by minus. So that's going to be the minimum directional derivative. It's going to be equal to minus square root of 8 times e to the 4. And then it's going to occur in the direction of the following unit vector, which is going to be equal to minus this unit vector, so that's going to be minus 1 square root of 2, 1 minus 1. So this is the same as just changing the signs on that. Minus 1, 1. So that's the direction in which the minimum slope or gradient occurs, and that's the magnitude of that minimum slope. So hopefully this is giving you an idea of what directional derivatives are and what they can be used for. And I find that this concept is really useful, especially for when you want to find specifically at one point along the surface in which direction you have the maximum slope and what is the maximum and minimum values of that slope based on that gradient vector that we construct from the surface itself. And in the next video, we're going to be talking about some more applications of partial derivatives, but we're going to talk about like branch multipliers, and we're going to talk about how we can use them to solve optimization problems that contain several variables.